I'm Ben, and my supervisor Marianne. We're based at the University of Technology in Sydney. It's pronounced Comirit. I want to use this talk not to go into the technical details of my paper, but to really just motivate the high-level reasoning behind my work. And I'm going to start off by talking about what it is I'm trying to do. My long-term goal is really to build not intelligent agents, but to build intelligent middleware and infrastructure, build the platform upon which intelligent systems can be built in weeks or months as opposed to years or decades. And the kind of intelligence I'm focusing on first is know-how, how to interact with the world, how to navigate, how to deal with a novel object, as opposed to more factual or other kinds of intelligence. In the long term, I want to look at using this know-how and this intuition about the real world and apply it in more business and purely symbolic systems so that the symbols have a deeper meaning. And what inspired me to go down this path was actually a paper in the logical Commonsense world, where the author tried to describe, using logic, what happens when an egg's cracked. It's a simple problem, but the paper was this long, complex paper with 60 axioms that really are quite complex. I mean, this one here says, if the container contains an object at a given time, and that container is facing downwards at that time, and the object in the container at that time is a liquid, or the object's a shape which is smaller than the lid of the shape of the container, then a fall initiates at that time. I mean, to me, this is ridiculous. It's not natural. And I really wanted to find a better way. And in my search for a better way, I really am guided by philosophy that I think we as computer scientists understand computers well. We've got all the parts we need. The trick is really in bringing them together and putting them together in the right way. It's sort of taking what we've got and harmoniously putting them together and reinterpreting old techniques and putting in the new applications. Which brings me to Comirit, which is my project. And my very first step is just integrating two simple techniques. The first is graph-based simulation, which provides for sort of iconic, visual, imaginative form of reasoning, and tableaux-based logical deduction, which complements this iconic representation with more abstract and symbolic reasoning, deduction, and it allows it to reason backwards. And the two techniques are intended to complement each other. What I'm going to do for the rest of this talk is briefly introduce each, and then I'll finish off by explaining how to put them together. The full details are in my paper. So I chose graph-based simulation because graphs are very general. You can use graphs to represent really anything, any structure, and any structure from 3D objects to social networks to document structures. And on these graphs, I apply annotations and use those annotations to simulate a wide variety of problems. So, reverting to this egg example, which inspired me to go down the path, we could simulate an egg. We could build a simulation of an egg using a graph by having nodes which represent sort of molecules, connect them with edges, sort of bonds, and then each node and edge really has just properties. They've got x, y, z coordinates, they've got local mass, they've got local rigidity and strength. And we can use this graph-based representation to just simulate what could happen. Over time, if we drop the egg onto a table, it will fall, it will crack, and the goo on the inside will make the table wet. I mean, the advantage of this approach is there's a very natural way of expressing it. Rather than these 60 rules that don't really say much, that are hard to encode, we've got 9 very simple common sense rules. These are rules that are taken straight from the high school physics textbook. They're not hard, and they're largely orthogonal. Gravity works on everything. You don't have to worry about the rigidity of a solid to apply gravity. It's just combined additively. So I think this is a more natural way of capturing a whole lot of very real-world type of knowledge. It's a lot easier than logical, expressing things in logic. Which really brings me to the second side of things. There are problems that aren't very well expressed in simulation, graphical simulations. But that work fantastic in logic, and we've seen many, many successes of logic in the past, although it hasn't given us true intelligence yet. It allows us to do the high-level symbolic reasoning, the abstract reasoning. We can use logic to infer possible causes and then simulate to see whether the causes match the reality. And to do this logical deduction, I've chosen the method of analytic tableaux. You'll see why in a moment. But the advantage of analytic tableaux is that it's a very efficient form of reasoning on typical problems. Its worst case complexity, depending on the logic, may not be fantastic, but its average case complexity is pretty good in practical problems. I mean, it's achieved great success in the semantic web on massive databases. And the basic way that this method works is that it uses simple rules and it operates on the syntactic structure of a formula. It just does syntactic manipulation on the formula to divide the space of worlds. It analyzes the space of all possible worlds to try and find worlds that satisfy or act as countermodels to a formula. Now, there's a fairly technical explanation for it, but the way I intuitively see it is we start off with a formula, and we start with this space of all possible worlds. So that's the blue box up here. We've got a formula, which is really asking whether it's possible to move a cup of coffee without making a mess. And we've got a space of all possible worlds in which that we want to see if this formula can be satisfied. And the method of analytic tableaux just breaks down this formula and uses it to guide the separation of this space into subspaces. So as it analyzes the formula, breaking it down into its components, we're also narrowing down the space of possibilities until we can't go any further with syntax alone. Which brings me to the key insight. We've got two methods here. The method of analytic tableaux, which really is a search over spaces of possible worlds, searches over spaces of scenarios. We've got simulation, which takes these possible worlds, takes these scenarios, and basically introduces consequences of it. It predicts the outcomes of these worlds. So these two methods are talking about the same thing. They're talking about these possible worlds. And that's the insight which I think leads to a more natural integration between these two methods. So reverting back to our worlds model, we have those two branches left, and we can, into those branches, now load 3D simulations of our cup of coffee and see, well, one coffee, the slow moving, was able to successfully move the object without making a mess, whereas the other cup of coffee under the fast move ended up making a mess. Yeah, so that's the basic idea, and I'm going into all the details in my paper. But the trick behind this, the real, I think, elegance of this approach is that it leads to a really nice implementation. The trick to making this work well is to make it absolutely simple, and you do that by putting absolutely everything in the tableau. Not just the logical formulas, the logical terms in traditional tableaus, but I load the simulations themselves, the data structures of the simulation into the tableau, and I even go so far as almost metaprogramming. I load the Tableaux algorithm itself into the Tableau, which means that the Tableau can use different logics in different parts of its reasoning. It can use different heuristics. It can use different rules in different parts of the problem. Yeah, which really that's my paper in 10 minutes. And in future, I'm looking towards more general forms of intelligence. And so, at the moment, I've been looking at integrating other forms of logic into this world-based idea. I've been trying to learn these 3D models, have the system automatically acquire these 3D models, and acquire an understanding of the parameters that drive these models just from experience. And finally, I've been working with a cognitive scientist trying to wrap this up and draw insight from biologically inspired cognitive models, cognitive architectures, to make this more richer. So, yeah, thank you.